Thanks, Inku. So I'm going to deliver 2 lectures. I'm not sure about the second lecture topic, but definitely it will be disconnected with the first one, which better I know what I'm going to talk about. So the project, first of all, I should say that the project that I'm going to talk about today is joint with Ayala Arad. I guess that most of you don't know her, and I'm used, whenever I present a paper which is joint with co-authors, I'm used to present the picture of the other person. So here is a picture of Ayala is actually here, and the location is our lab. Our lab, namely, of course, it's a cafe in Tel Aviv where actually we work usually. And that's one of the places where we thought about this paper. If you don't see her in this lab, so here is another lab, and she is here. That's actually, that's also advertisement of for Jerusalem. That's the open air market in Jerusalem, a wonderful place for to spend the evenings in Jerusalem in the summer. So that's Ayala Arad. The project that I'm going to talk about today for me is a bit special because I'm an economic theorist, and actually that's probably the only paper of mine up to now and probably ever that was inspired by experimental work. I did some experimental work for reasons that I'm not going to talk about today, but usually I'm doing it completely separately from the models that I'm dealing with. But that's actually probably the only example that we were inspired by experimental work. And therefore, also it's early in the morning, so let's start with something light. And we spend the first 10-15 minutes on the source of the inspiration. So I guess that most of you have heard about the Colonel Blotto game or games, but in any case, let's remind ourselves what is this game. And that's more or less the text that participants in some experiments received. So imagine, everything starts with imagine. Imagine that you are a commander of an army during wartime, which is about to do battle with the enemy's army. Each commander decides how to allocate his 120 troops across 6 battlefields, and the battlefields are ordered 1, 2, 3, 4, 5, 6 from left to right. In a particular battlefield, the commander who assigned the larger number of troops wins the battle. Both of you lose in the case you assign the same number of troops to a particular battlefield. Those of you who have never seen it, or even people who have seen it, I just would like to pause for 30 seconds and just, I promise not to embarrass you. I will not ask you to suggest strategies, but please just think about the situation and establish in your mind a strategy that you might play if you were participating in such an experiment. Okay, there is a reason that will be very clear why I pause for 30 seconds. Let me, before we continue, let's say the Colonel Blotto game is very old game. It goes back, soon it will celebrate its 100th anniversary. It was invented by not less than the famous mathematician Borel in 1921, and it was translated to the Western world by not less than Savage in 1953. The Borel's game was a bit different than this one. I mean, he was talking about continuous variables, and he analyzes for the case of 3 battlefields, but basically, of course, this is the source of the Colonel Blotto game. Now, the version that you see here is a bit, it's not completely standard because there was one change that we did in this experiment. which was in the last point. Usually when there is a tie in a particular battlefield, then people take it as 0.5 points get to each of the players, which makes it, of course, a zero-sum game. So this situation, as described here, is not exactly a zero-sum game, but it's almost a zero-sum game, and we put it actually because we wanted to increase the motivation of people to avoid the strategies that probably comes first to your mind when you think about this situation. And I bet, and I have good reasons to bet about it, that most of you, even here, and most of you, even if you are economic theory students, thought first about 2020, 2020 as a sort of anchor to the thinking about such a situation. Now, when you start, so the game is actually very simple. It could be described in few words, but if we analyze it in standard game theoretical, using game theoretical tools, actually it looks quite awful. Why? Because the number of strategies is huge. The number of strategies in this game is something like 250 million. And even if you ignore the geography of the battlefields and you just think about, you identify permutations of a strategy, you have something like 400,000. Now notice, of course, something that all of us know very well, that the language of game theory is a language of thinking in terms of strategies. We are saying the basic statements of the solution concepts that usually we use is a strategy A is the best response against a strategy B. A strategy A is the best response against some distribution of strategies of the other players. I delete the strategy A because it's dominated. All the terms that usually we use in game theory are about strategies. Our observation or the lessons that we draw from the experiments that we ran, Ayala and me, and also thinking about this game quite a lot, and also some other stuff that I will describe in a second, is that this is in some fundamental way a wrong way to think about, for us to think about how people think about such situations. Because now my bet again, even about you, is that probably the only strategy that you really thought about explicitly was the 20-20-20, uniform 20. But then when you started to think, then you started to think about properties of strategies and not about strategies themselves. And the first thing that probably came to your mind was to some sort of, you thought about a decision whether in how many battlefields to focus, or what we call in the paper to reinforce. And probably it came to your mind first that actually probably you should not, of course, you cannot reinforce the 6 battlefields. So you started to think about probably to reinforce, of course it's silly to reinforce only 1 battlefield. So probably you started to think about reinforcing 5 battlefields. Probably, and now comes the key point, which is you thought about, okay, but the other people will reinforce 5 battlefields, probably it's a best response, or it's not a best response because best response is about strategies. But something best response, we call it in the paper proper response, that actually reinforcing 4 battlefields is in some sense a good reaction to other people reinforcing 5 battlefields. Now this stage is a key to the strategic thinking in such situations, because the intuition that, again, I have a good reasons to think that most of you, most of us, most of the participants, the subject in these experiments have in mind, namely that reinforcing 4 battlefields is a good reaction to reinforcing 5 battlefields is not based on a very clear calculation. But it is a sort of heuristic that we have a strong intuition that it's correct, and we have some sort of guesses how people get to this calculation. But it's some fundamental component of our thinking in such a situation. But notice, no strategies here. It's the characteristic against characteristic. The property of strategies is a good, best, proper response against characteristic. So our point actually, and I would like very briefly to tell you about some of our results from a paper, the experimental paper that was published in JIBO a few years ago, and it's, as I've said, this inspired the theoretical paper that I will talk about today, was that people are in such situation. First of all, notice many people in experiments, many people, first of all, don't think. Such is life. Second, they might think, but they don't think strategically. That's another illusion that in game theory automatically we take all players think strategically. That's not correct. Some people don't think strategically. Some very important people don't think strategically, by the way. And second and third, even if people think strategically, they don't think in the mode which is even close to the mode that is captured by game theory. And they do think in terms of properties, and the three properties that we identify in the experiments are the following. I should say that we ran the experiment online. All my experiments are online, and the experiments that I was involved with usually do not have any monetary incentives. That's for another lecture, why that's the case. But in any case, we're using here actually two data sets. One data set, we call it classes. Some of you probably have seen, came across probably at the undergraduates. I have some websites that celebrate now the 15th anniversary or 16th, which is called gametheory.tau.acil. That's a website where teachers of courses of game theory can use it to offer a sort of survey questions to students. They get the data about their own class versus the entire world. Again, it's for another lecture to explain why did I do it. But I guess one of the games that was posted there was the game that you've just seen, the Blotto game. And at the time of that we wrote the paper, I had already about 4,600 subjects from many places, 25 countries, for many groups participating in this, responding to the Blotto game. Second, we had also few years ago, an Israeli newspaper, which is a sort of a daily business type of newspaper, gave us the permission to distribute among his readers a text which is similar to the one that you've just seen, and we got about 2,000 subjects, readers of the newspaper, responding. I should say that in the Calcalist version, in the newspaper version, actually what we put the questions that we put to the readers was that their strategy is going to be played against all other strategies. So actually what we ran is a tournament, round-robin tournament between the readers, and actually when the calculations, we also treated the classes in this way. Okay, and now the main dimensions that we found that were considered by the subjects, and again, I will not get into the details, but I will give you some very few hints. Why did we conclude it? Well, the first thing that so the first dimension that we observed that many, not all, but many subjects were using was the number of reinforced battlefields. Our definition here of reinforced battlefields was using more than 20 troops in a particular battlefield. But that's not the only dimension. The other dimension was use the location. Now, from game theoretical point of view, pure game theorists, probably we say that there is nothing, I mean, the 6 battlefields are completely symmetric, and there is nothing to distinguish between battlefields 1 and 4. Psychologically, that's very wrong, because people, and we have a lot of evidence, that people treat the location as a very important factor in their strategic thinking. And the question whether to, if I decide to reinforce a few battlefields, whether to put them in the edges or to put them in the center, whether to avoid the edges or whether to avoid the center, is a clear dimension that many of the participants were thinking about. And the third dimension that we found very common is regarding the unit digit. Namely, it comes across of some individuals, not everybody. I mean, the default is actually to take the 120 troops and to divide them into multiples of tens. But then it comes across to some of the people. And that actually that's not a very good idea, and it may be actually a better idea to put some ones and twos, especially if I intend to put 0, then it's actually, I will beat, with a little expense of 1, I will beat all the other guys who put 0. And also if I put 30, then it's maybe actually a better idea to put 31 in order to beat the 30 that is going to be very popular. And probably it's better to put 32 to beat the 31, and so on. Not so on, actually. That's the end of the K-level reasoning usually ends with 2. So that's the 3 dimensions that we find very common. I should say that Ayala continued this experimental work with Stefan, and I never succeed to pronounce his name correctly, with Stefan Penczynski. I'm sure I don't pronounce his name correctly. He is from University of East Anglia now. And what they did, they actually did they ran sort of with laboratory, with the proper experimental, using the proper quote-unquote experimental procedure, with the following idea that actually every player was divided into is actually a team, and the players exchange some messages to persuade the other player to use about some arguments why to use a particular strategy, and then they can actually analyze the text using some machine learning also and without machine learning, and to identify the considerations. And basically, with a small caveat, actually, these are the 3 dimensions that they found also very common. And what is probably interesting is that there is no other consideration that appears in the explanation beside using these dimensions. But notice again, there is its dimensions, and it's not talking about strategies. I promise you some hints about how did we get to these conclusions. And again, also if you are interested, you can read the Jibo paper. But here are two it's almost a rhetorical tricks that now I play on you. Here are 2 examples to what I've to the data, to the evidence that we have to persuade you that that's the case. If I need at least, I probably first of all in introspection, I'm sure that you notice yourself that when you thought in the 30 seconds about this problem, you actually used probably some of these dimensions and not anything else. But here are So here are the winners of the 10. Again, we ran the classes as a tournament. We ran the Kalkalist, the Israeli newspaper, as a tournament. And here are the 10 winners. The 10 winners, namely the 10 strategies that got, on average, the highest number of points. The score, which is the average in the tournament, you see here. And here are the 10 winners in each of the tournaments. By the way, up to these experiments or up to this calculation, I thought that a 0 probability event does not happen. And here is the first case and last case in my life that I've seen 0 probability event happens. Here is the winner in this tournament, and here is the winner in this tournament. And surprise, surprise, it's exactly the same strategy. From the 250 million strategies, it's exactly the same strategy who won here and here. I'm a very skeptical guy by nature, and one of the thoughts that I had was that actually it's the same guy. So I checked, no, it's not the same guy. There's 2 people from different countries and never met or discussed or whatever. So in any case, these are the winners. But by the way, it's not only one, but actually 4 of the strategies, 4 of the top 10 in the left tournament are the same as on the right. But that's just curiosity. What is more interesting for me is look at the strategies. These are the strategies which are the winners. And look at them, and you don't need any statistics, you don't need any explanations to see that the 3 dimensions that I described are playing an important role. It cannot be that somebody decide about add in mind 2, 31, 31, 31, 23, 2 as a sort of a basic to his thinking. So it's very clear that from this, what people thought, first of all these strategies reinforce 4 battlefields. All of them, almost all of them, ignore the edges. I mean, they put lower numbers on the edges, not completely ignoring, but and not completely, and that's the 3rd dimension. Namely, it's very clear that there is an overuse of the digit unit 1 and 2. So this is, of course, that's not, by the way, I'm saying that it's a bit rhetorical, because these are the winners. This is not a sample of the strategies. Many strategies, many people, I don't remember the exact number, but something like 8% of the participants use the strategy 20-20-20-20-20. And there is even something like 2% of the subject who were using the very, very clever strategy 120-0-0-0-0. So, but when people think, and when they think strategically, and when they win, then you do see very clearly the use of the 3 dimensions. So let me give you one example which I love, which is after the tournament in the Israeli newspaper, then I wrote to the guy who won the tournament, and I congratulate him for this big achievement of his life, and asked him for permission to print his name. And also I asked him to explain how did he get to this strategy. And this is basically a translation from Hebrew from his explanation. And I wouldn't say that that's a typical text that you get in Ayala and Stefan's work, but that's more or less what we get, also, they got also in their written explanations. So that's what he wrote. In the first stage, I decided I would surrender on 2 fronts. So that's exactly what we predicted, namely that first of all, people think about the battlefields. By the way, one of the first times that I presented the General Blotto game, it was in front of the late Reinhard Zelten, and one of his, I think, good comments was immediately that actually the order of the use of the dimensions is important. And actually that it's not by chance that the first thing that it comes to mind of people is the number of 4 battlefields and not the other 2 dimensions. But that's another matter. In any case, in the first stage, I decided I would surrender on 2 fronts. He talked about the number of surrenders and not about reinforcement, but of course that's equivalent. But not so easily. I thought that other people would decide to assign a few battalions to some of the fronts and perhaps would not deploy any battalions to other fronts. So I could win on an abandoned front at the inexpensive price of 1 battalion. That's the 3rd, actually, dimension that I mentioned. Eventually, I decided to deploy 2 battalions on the weak fronts in order to overpower anyone who thought like me and place 1 battalion on the weak fronts. By the way, here actually what he's using, a very typical K-level reasoning type of thinking, but notice it's absolutely not the standard K-level reasoning that you see in the works that is very popular this day, because it's not in K-level in the language of the strategies. It's only K-level in the level of the dimensions. And it seems, now he uses the term, it seems logical to me, which is funny a little bit, but that's what he wrote. It seems logical to me that the weak fronts would be on the edges. Again, that's the 2nd dimension that I mentioned. So all the 3 and nothing else appears in his explanation. You may say that you don't need even the text to see it because you see it from the strategy. But in any case, it's nice to see this explanation very explicit. I should also say that this game, the Blotter game, was analyzed not only by Borel, but in the last 10, 15 years, there were two papers. Actually, the most noticeable is always about Sergio Hart, very precise, very comprehensive analysis of the Nash equilibria. The mixed, of course, there is no pure Nash equilibria for this game. There is only mixed Nash. And following another work that was done earlier by Robertson, but Hart, as Sergio has a full characterization of the Nash equilibria of this game. We will come back to it later. Okay. So where are we now? So again, let me repeat on the message on what we got from the experimental, or looking at the experimental data. The main insight or the main conclusions that we got is people don't think in the not only not like Nash, and not only not like the standard K-level reasoning, but the basic language that they use is completely different. And therefore, by definition, game theory is out. And now we have to do something else. And what I exaggerate a little bit, of course, of course, our scope from now on are games is similar in nature to the Blotter game, namely, and the characteristic of these games it's not 3x3 game, it's not 2x2 game, it's not the prisoner's dilemma. It's not games where the set of strategies has a very clear structure, like, let's say, the hoteling game. So you can say it's infinite number of strategies, but the strategies are ordered very clearly. It's games which, as the set of strategies is a bit more complicated, and the number of strategies is not very small. And then our conjecture is that in this case, people think in terms of dimensions and characteristics of the dimensions. And the target of, and now I move to the goal of this project, that I report now on is Rani was using yesterday the word framing, to have some new frame where you can build new models, and I will use the same terms. Namely, what I'm going to present now is a sort of a framework that is capturing some, at least, of the ideas that I talked about up to now. And mainly what we wanted to do is to construct some sort of framework that will be parallel to the framework of Nash equilibrium. Namely, I think about Nash equilibrium as some sort of a stable description of the situation. Stable in the sense that players don't have a good reason to deviate from the norm of behavior that the Nash equilibrium dictates. And here we will have something similar, namely we want to have a sort of a frame that will allow us to define some solution concepts that will be parallel, but parallel in the sense of that there will be some stable norms, but on the other hand, they will be stated in the language of dimensions and characteristics, and not in the language of strategies. That's the goal. I should say before I continue, and it's not apology, but although it may sound like that, there are many ways to do it. And we are not claiming by any means that this is the way to do it. It's a way to do it, and you may object it, and you may think about other ways, and you're welcome to think and suggest alternatives. And I will talk about some alternatives myself. But a way to do it, let's do it. So, a theory, a model. So, the basic ingredients that we will have in the model is a two-player symmetric game. Why we talk about symmetric and not asymmetric games? Because it's enough to present, it's simple enough, and the meaning of a norm of behavior is clearer. We don't have to talk about norm of behavior of player 1 and norm of behavior of player 2. It's one norm of behavior So it's just easier to talk about it. And I don't think that there is any value to expand it now, at least in the first presentation, into asymmetric game. If you are insisting on that, there is in the paper, in the last section, there is some example which we do it. Okay, so a symmetric game, to remind you, just the notation, the symmetric game, there is a set of strategies, actions, S, capital S, and there is a pair function or utility function U, and the meaning of U, just to avoid any confusions, U means, U of S, S prime, means that's a pair of a player. It doesn't mean, again, there is no player 1 and 2. F of a player, if he uses the action or the strategy S, where his opponent is using the strategy S prime. Okay, so that's actually the full description of symmetric game. I will not get into technical details. These are really not interesting here. But if you want, think about S as to be finite, or think about S to be infinite. But if U being a continuous function or something like that, that's absolutely not important. But this is not the model that we will deal. This is only the basic ingredient, because I talked about dimensions and so on, and we are not shy to expand the model. I'm saying it because of a reason that we will talk about it later, which is, I think that, okay, we talk about later. So let's do the expansion. The expansion, instead of speaking about a game, we talk about what we call an edited symmetric game. The term edited, by the way, we borrow from, again, I mentioned Zelten. In general, by the way, this paper, I think, is very much in spirit of the ideology, let's say, that of Zelten's work. So an edited game is the following. By the way, Zelten was using the term edited in a different sense. For Zelten, actually, he was emphasizing something which is very, in some sense it's trivial, in some sense it's deep, which is that even a game is usually not well defined. There is a situation in life, and we edit the situation into what we call a game. It's only in laboratories that people play games. In life, there is no clear game. There is a stage of editing, which psychological stage or cognitive stage of editing into the situations that we describe. So in any case, the edited symmetric game in our paper is the following. There are two components, two ingredients. First of all, there is a symmetric game, the SU. But now we add to the model another component, and that's the component that is the DK. Now, what are the DK? The letter D is for dimension. K, but actually the dimensions themselves are the small k. There are capital K dimensions. And K is actually, the small k actually is the name of the dimension. What is dk? Dk is a function. Now, there are several ways to do it, but the one that we eventually did in the paper was the following. Dk, what is D3? D3 is regarding the third dimension, regarding dimension number 3, D3 of S, a strategy S, is the value. But the value does not have to be a number, but it's a value that the strategy S, or the characteristics that the strategy S gets according to the third dimension. So, for example, if 3 is the dimension of the number of reinforced battlefields, so D3 of 40, 40, 40, 0, 0, 0 will be 3. And D3 of 0, 0, 30, 30, 30, 30 will be 4. Okay? So that's the characteristic along the dimension that the strategy gets. But of course, you are aware, of course, that basically what is important is that the DK dictates or induces a partition of the strategies along the dimensions. So it's partition along the 0 reinforced, 1 reinforced, 2 reinforced, and so on. Okay? And now, so each of the dimensions induces a partition, and we can talk about the meat of the partitions. And the meat of the partitions actually is, or a member of the meat of the partition is a cell. we call it a cell. So what is a cell? A cell is a set of strategies that gets, along all the capital K dimensions, gets the same characteristics. So a cell will be, I reinforced 4 battlefields, I use only the multiples of 10s, and I ignore the edges. So this will be, all the strategies of this type will be in this cell. Okay? A picture that a beautiful picture, which I am proud that I drew, is this one, and actually in some sense you can see better what is going on. So every X is a strategy. Every X is a strategy. In this picture, there are 2 dimensions, D1 and D2. So what about this strategy? This strategy, D1 of this strategy is capital D, and D2 of this strategy is 2. This is a cell, so the cell D2 contains these 2 strategies that share the values or characteristics in all dimensions. Cells might be empty, that's fine. They don't have to be, some of them could be empty, that's nothing wrong with that. Okay? Now what we are heading to? We are heading to a solution concept that will, the statement that we look for will be something of the type B3 is the norm of behavior. We are not heading to something like game theory usually is trying to do, to say that a particular strategy is the norm of behavior, or that the distribution of strategies which such and such is 1/3 A, 2/3 B, or whatever, is a norm of behavior. We are not going towards that. We are going towards just saying something of the type B3 is in some sense equilibrium. Okay? And I think that we find it very, very plausible that in this sort of games, you don't, if there is any stability in behavior, it's not a stability of a very particular distribution of strategies, but people feel that they how to play the game to reinforce 4 battlefields. That's a sort of something that very likely to be a sort of a stable behavior in a game like the Blotto game. Okay? Now, let me already use the word prediction, which game theory tends, or economic theory tends to use a lot. That's a word which, for me, it's a dirty word. I don't want to predict. I don't want you to predict me. If I would have any power, I would suggest to put some regulations on predictions. I think it's a terrible fact that people might, and luckily, game theory does not have any good predictions about anything. So, but I don't want to predict. So whenever I will use the word predict is quote unquote. It's almost satirically. But if we have any prediction here, the prediction here is a prediction of a cell. That's what we are heading to, and not anything like we are used in game theory, namely not a particular strategy and not a distribution strategy. Okay, let's continue to use this diagram. So now, in what sense we feel we can say how to formulate an idea that B3 is a stable mode of behavior? Now here comes 2 points that rightly or wrongly we combine in this paper. As you've seen, the name of the paper is Multidimensional Thinking, and the multidimension up to now, I emphasize only one thing, which is the dimensions dictate the partition of the partition of the strategies. They determine what is a cell. That's the language that we can use. But we would like actually the main solution concept that we talk about in the paper is called the MD equilibrium. That's also use the dimension about as a sort of the sphere on which the strategic thinking is going on. What I mean is the following. So B3, in what sense B3 will be in our approach will be stable? If, and now comes the explanation to the last point, we assume that players think about the dimensions separately. It's not necessarily. We could think about that people think about the norm is B3, but Michi is thinking about actually using C4. So he's changing the values in the 2 dimensions, maybe. But our main discussion in the paper is about the second idea of the paper, which is that people are thinking about each deviating from each in the dimensions separately. So the other player, my opponent, is going to play B3. That's known. That's the common knowledge of the solution concept. I'm now thinking about deviating from the B3. I'm thinking about changing the B. So I'm thinking about moving from B3 to probably C3 or D3. I'm also thinking about moving from B3 to B4 and to B5. In the MD equilibrium, I'm not thinking about moving to C4. Okay? So again, dimensions get here in 2 ways. Number 1, they define the cells. Number 2, they define also the dimensions along which we are thinking. This separation is not necessary, and we talk in the paper also about what we call global equilibrium. In the global equilibrium, we use the dimensions only in the first sense, namely only as the language of the cells, but we absolutely allow the player to think about deviation from B3 to C4. Okay? So if you don't like the multidimensional, you can think about it as the global. By the way, which is like actually think about the paper about the solution concept as ignoring the dimension in this respect is like actually thinking about one dimension. So take all the cells, put them on one line, and that's actually give you the okay. Okay, and now we come actually to the key modeling question. So I would like to say B3 is equilibrium. I am thinking about moving to C3. What sort of consideration I have? Our assumption here is that if there is any common knowledge, is that players play B3, but we do not, the players don't collect any statistics about what are the strategies within B3 that are used. We just know that players play B3. I'm thinking about moving to C, and the formal concept that we are defining in the paper is that for equilibrium, it has to be the case that the value B is a proper response along the first dimension against B3, given actually that the other value that I'm using is 3. Okay, so we have a sort, we need to define to say, yes, C is actually a proper response to B. Right? C is a proper response to B, or if you want, C3 is a proper response to B3. That's something that we have to add. And now the question, how to do it. Now, in our mind, we think about it that actually what people have is they have some sort of intuition, heuristic, or whatever you call it, that captures this basic idea. But there could be 2 ways. Number 1 could be to add to the paper, actually to add to the model, to add some sort of this heuristic as an ingredient, as a primitive. We chose a way which is probably more mainstream, which is to define this as a part of the, not to take it as exogenous, like we took the dimensions, but to define it within the model itself, and we do it in the following way. I don't know what you're going to, and sorry, let me say again before I do it, before you will complain, or before I complain, it's not the only way to do it. It's just one way. And the one way that we suggest is the following. I think you play B3. I'm thinking about moving to C3. There is now asymmetry in our thinking between you and me. I don't know what you're going to play in B3. I'm assuming, since I don't have any idea what you're going to play in B3, I take it as if you are going to play uniform mixed strategy on B3. I'm asking myself, what is the best response? And now it's a regular best response against uniform B3 in this in strategy B3. I compare it with the best response in C3 against uniform B3. What I will say is that C3 is a proper response to B3 if actually when I'm thinking about moving from B to any other value along this row, I found the best response, the standard best response against this uniform on this cell, that it exists in B3. And I think that I'm saying that I would like to move to C3 if the proper response is in C3.
So uniform distribution is a complete absence of any prior knowledge.
Right. It's absolutely, it's in the standard Laplace, etc. tradition, and it's used in game theory actually in several ways, including, by the way, in the K-level reasoning definition.
That's a strategy.
Right. But again, that's a standard best response in a strategy, but let me emphasize, we think about it again, I'm repeating myself again and again because it's important. That's just a sort of explanation for heuristic. Heuristic, we believe that you have in mind that C3 is or is not a proper response to B3. But the formal definition or the foundation for this heuristic is that you find a strategy in C3 which is a better against uniform B3 than any strategy in B3. Now, as I've said before, it's not the only way. Let me give you immediately another possibility which I found very attractive to define it, which is through the representative strategy. Some psychologists talking a lot about what is representative strategy. And for example, to reinforcing 4 battlefields, I think that the very representative strategy that we have in mind is a permutation of the 30, 30, 30, 30, 0, 0. Right? So another possibility could be that since I don't know what Inku is going to play in B3, I'm thinking about it that he's going to play as if, I know he will not play this strategy, but I'm thinking as if he's going to play the representative strategy within B3. And now I'm thinking about what is the best response against this strategy, particular representative strategy. Okay. Now notice what we don't do. We call it in the revision of the paper that we write now, uniform versus uniform. We don't assume that when I consider C3 versus B3, I don't know what I'm going to do, and I don't know what you're going to do, and I'm comparing the uniform C3 against uniform B3. That's another possibility. I think it would be quite a boring possibility because it will collapse the analysis to standard Nash of finite game. But I think it also does not capture important factor, which is it's very different when I think about my action versus when I think about your action. When I think about C3 as my action, I might think about particular strategies within C3. Where I think about your strategy, it's more likely that the vagueness creates some sort of uncertainty about what is inside B3. So let me conclude, and then let me now define what is equilibrium. MD equilibrium will be a cell such that actually, what I've said is equivalent to the following statement, that a best response against uniform on B3 among the strategies that differ only in one characteristics is inside B3. A global equilibrium will be a cell such that a best response against uniform B3 among all strategies in the game is in B3. That's the global, and as I've said, usually we talk in the paper about the MD equilibrium. Yes, please.
In the Camel plot example, okay, is it easy to calculate eventually flight uniform distribution of
No, at least not for us. But the way, the interesting, it took us quite a while to prove it. You know what is the uniform distribution against all strategies of Blotto? I mean, the entire cell. You see, but if you would think about it, I'm sure you will find the answer, but the proof takes some time. It's the uniform distribution, the 20-20-20. That's actually the best. But you know, it's not, I don't think it's trivial. Okay. Okay, so that's the definition. I mean, the formal definition is here, but it's quite boring. I think that it's the idea should be clear, or if it's not clear, please ask at this point. Okay, probably to clarify. Sorry. Before I clarify, let me just some related literature, which I feel that I should mention. First of all, there are very few solution concepts in game theory, standard game theory, where the solution concept is a set and not a distribution of strategies. One noticeable exception is a paper by Basu and Weibel from 1991. The paper is very, very different from ours, but it's definitely in their solution. They have a sort of a notion of, they don't have a cell, but they do have definitely a solution concept, which is a set of strategies, which has some properties that we will not talk about now. The idea of the multidimensional is actually a main theme of something very old that probably was forgotten by most economists. There was many, many years ago, two great economists, Marshak and Radner, were working on what they called a team theory. The team theory, the idea was that a player is an organization, and the organization, there is no particular person if you're not North Korea. So it's not a particular person who makes all the decisions, but it's a sort of different people are making different divisions of the firm or the organization makes different decisions, and that's what they call the team. So all the players in the team, that's their assumption, is that have the same goal, but different players, different agents within the player decides about different characteristics. And so that's actually basically what we have in mind in the multidimensional thinking, and that's something which definitely is already in Marshak and Radner. The idea that Radney was talking a little bit about it, about the work of where actions or beliefs are framed in terms of categories rather than strategies, that's a theme, actually beliefs, that's a theme that appears in there was an old paper by Michele Piccioni and me, but of course the person who did a lot in this direction is Philippe Yechiel in his concept of analogy-based reasoning and the principle of indifference I mentioned. Okay, example. The first time that I presented this paper, it was in Jerusalem in front of Bob Aumann. Some of you have seen him, and he's a very right-wing Israeli. I am quite a left-wing Israeli, and so in order to tease him, we invented a game that we call the settlements game. So as we wrote here, it was invented by the Israeli government and just formulated by us. If you have never seen what is a settlement, that's a typical settlement in the West Bank. And that's more or less the end of the politics. From now on, it's the game theory. It's a sort of Israeli internal joke. If you don't get it, it's fine. So the game is the following. Imagine that you are playing a game with another player. You and the other player are presented with 5 territories ordered in a row, 1, 2, 3, 4, 5. There are 5 districts in the West Bank. So each of you is to choose either one territory or a pair of adjacent territories to settle in. The Israeli government chooses 1, 2, 3, 4, 5, but that's another matter. So there are 9 strategies here. 1, 2, 3, 4. So there are 9 strategies. 1, 2, 3, 4, 5, and 1, 2, 2, 3, 3, 4, 4, 5. Now, 9 is not a big number. I had a teacher in mathematics when I was undergraduate, Micha Perles. He was a combinatorics mathematician. And he made a statement that made a lot of impression of me, because which was that 17 is half the way to infinity. He's absolutely right? 17 is half the way to infinity. So 9 is, I don't know, 1/5 the way to infinity. So it's not very large. And it's a border case, probably, between the case that we think in dimensions or we think in strategies. But, of course, for the example, it would be enough. Now, let's continue. So in the case that the territories chosen coincide or overlap, so then there will be a clash, a war, and neither of you will get anything. In the case that they don't coincide or ever overlap, each of you keeps the territory or territories he chose. The value of holding one territory is $2 billion, and the value of holding 2 million territories is $3 billion. Okay? That's the game. Is it clear? So it's a sort of a territory games. I've not seen it in the literature. If some of you know about previous papers that had this type of class of games, I will be pleased to see. I will not be pleased to see, but I will acknowledge. Okay. Okay. So that's the game. That's the game. It's not of course it's not a zero-sum game. But that's not the edited game. And there are many edited games. Again, let me emphasize, there are many edited games to the same game. And actually, we feel that this is one of the virtues of our approach, that the prediction, quote unquote, is not independent from the language that is used by the players to think strategically, namely the language of the dimensions. And here is one edited game, and the edited game includes the following 2 dimensions. Dimension 1 is the number of territories that you settle, which could be either 1 or 2. I think that this is a very natural dimension to think, even in small set of strategies that includes 9. And the second, which especially is true in the Israeli case, well, it's not a real question, but whether to settle in the center, which is the Jerusalem area, or not. Okay. So these are the two dimensions, and here is again, that it's not a game, although it's a matrix, but it's the partition of the 9 strategies into 4 cells. Is it clear? Okay. And now, just to train ourselves with the definition, this game has only one MD equilibrium, which is 2 not center. 2 not center is the only equilibrium. Let me just demonstrate the calculation a little bit. So you play 2 not center. The norm of behavior is 2 not center. What is the expected utility or payoff if I play the best strategy in 2 not center? That's a very simple example. It's not important whether I play 1, 2, or 4, or 5. With probability 0.5, there will be a clash. With probability 0.5, there will not be a clash. And therefore, the expected utility is 1.5. Clear? If I moved here, then it's the same, actually. If any strategy here will get also 1.5. If I move here, actually I will do worse, because if I choose a strategy here, then actually with probability 0.5 there will be a clash. With probability 0.5 no clash, but I get only 1 territory and not 2. So that's the reason that this is MD equilibrium. It's easy to see that that's the only MD equilibrium. This is not a global equilibrium. It's not a global equilibrium because actually the strategy if you play 2 not center, it's better for me to play 1 center, because then by sure I will get 1 territory, and under our assumption about the marginal utility of a territory, it's better than to get 2 territories with probability 0.5. So that's an example. How does it relate to Nash equilibrium? It's very different. Actually, it's not very interesting to analyze it, but let me just say that actually any equilibrium, any mixed strategy equilibrium that contains strategies in this cell must contain also strategies in this cell. So that's, and actually here you have actually the calculation of all the strategies, mixed strategy equilibrium. But that's, again, it's not very important. Okay? Questions? Okay. Now what to do next? Well, I have 31 minutes, so let me give you a brief description of what you can find in the paper if you are interested. What we did after this formalization is calculation of the mixed strategy, of the MD equilibrium for 3 games, 3 families of games, I should say, which has some economic content. So I will talk briefly about one of them. Why we did those? There are many games that you can do it. We did it because actually in those games we felt that indeed we can trace some relatively intuitive calculation, relatively natural intuitions related to the calculation of what we call the proper response. And then we'll talk a little bit about existence and so on. Needless to say, existence is not guaranteed here because pure strategy equilibrium is not guaranteed in regular games. Okay, so let's talk a little bit about a very simple version of the Colonel and Blotto game. It's not very simple actually, it's quite complicated. But instead of 6, there will be only 3 battlefields, like in Borel. But the number of battalions which each of the generals hold is capital N. Okay, so it's generals, it's a family of game because we do it for every n, or at least n, which is multiple of 6, but or 3 or 6, I don't recall, but that's the 6, I think. Okay, so actually in this calculation we did analyze it as a zero-sum game. So we assume that in the case of a tie, then there is a 50-50 split of the point between the 2 players. So actually every battle between one player and another must end with the results either 2-1 or 1-2 or 1.5 versus 1.5. Okay, these are the only 3 scores that could emerge in such a game. Okay, now we analyze this game as an edited game when we use the 2 very particular dimensions. The one dimension is the number of battlefields that are reinforced. Actually, in this calculation, we took reinforcement as being at least n divided by 3. And the second dimension relates to the geography, and that's the dimension that you see here. And the 3 values that we give to the second, so here you see the values here are 1, 2, or 3. The values here in the second dimensions are, so the second dimension, we call it order. Order, namely, we use some focal order. What is the focal order that we use, or not? So the focal orders here are, think about it, that you have already 3 divisions, 30, 20, 10 troops. Now the question is, given the geography, what is the order that you use the 30, 20, 10? Decreasing means decreasing. Increasing means increasing. And other means not increasing and not decreasing. And in this, given the 3 battlefields, it's a union of 2 families, which we call in the paper pick and sink. Pick means that the strongest is in the center, and sink means that the weakest is in the center. Okay, so that's the other, actually, the union of these 2 categories. You can, of course, split, if you want, other to 2, and the result will be a different edited game. And let me tell you, surprise, surprise, a secret, that if we do it, then if we split the other into 2 categories, then there will not be any MD equilibrium. So the reason that we put in the paper was also that we wanted to have an example with MD. Okay, is it clear? Okay. Now I will skip on the example here and let me move directly to the proposition. And the proposition is the following: in the edited Blotto game with 3 fields and n, which is multiple of 6, then the only MD equilibrium is 2 other. Let's start with the interpretation. What does it mean 2 other is MD equilibrium? For us, it means that it's a mode of behavior is that you are going to reinforce two battlefields. You are going to focus your troops on two, not on one, not three, only on two. And you are not going to use, I think that's the interpretation of the other, you are going to avoid a clear ordering. You are going to avoid a clear ordering. You are not going to use the increasing or to decreasing order. That's the mode of behavior that we calculate or we prove to be stable a la the definition of the MD equilibrium. Now, let me give you some hints about, the proof, I should say, it's, at least for us, was not easy. It involves quite a lot of combinatorial calculations. I read it again a few weeks ago, and I was amazed by ourselves that we did it. Actually, it's also, I think it's the first and hopefully the last paper of mine where some elements of the proof are in the appendix. I hate it, but it's really just a calculation, so we put it. But actually in the paper itself, in the main body, we put actually more the intuition. And let me give you some of the intuition of, I will not go through all the details, but some of the intuitions that are in the proof. So for example, why 2 decreasing is not equilibrium? Why 2 decreasing is not equilibrium? So I know that Inku is using, as everybody else, is using 2 decreasing. Namely, he put very high, high, and low in this order. Now, if I will battle him using the same strategy, some type of strategies, then I will get probably something like a little bit more than 1.5. But there is a much better way to fight against the 2 other of Inku if I will use actually a strategy in 2 other. And the 2 other would be a strategy not just in 2 other, actually a strategy of the type of 2 peak. Why? Against the 2 other, 2 decreasing, I will put very low, probably 0, against the very strong. I will put the very strong against is strong, and I will put medium strong against is weak. So I will most likely I will win in 2 battlefields. Whereas if I use a strategy in 2 decreasing, I will get probably a little bit more than 1.5. So that's the intuition that once I know the ordering that he is using in this type of games, I can use the order of use the same type of strategy in the sense of the first dimension, namely to reinforce 2 battlefields, but reorder it in a way that I will beat him. So when you think about it in this way, I think that it quite makes sense that any clear ordering of the other player should not be a part of equilibrium, a stable norm of behavior. What is probably, let me demonstrate a little bit another type of intuition that you have here, which is, we want to show that 2 other is equilibrium. To show that 2 other is equilibrium, what I need to show is that if I move the 2 to 1, I'm not winning. By the way, it's clear if I move to 2 to 3, I'm losing. But if I move to 2 and 1, I'm not winning. And it's also, I have to show that moving from other to something which is like increasing or decreasing does not help. And let me actually demonstrate the intuition behind that. So 2 other, the strategies in 2 other are split into 4 subclasses, which are exactly equally sized, which are, you see it here. These are that's a split of 2 other. So the H here is the very strong is in the center in these two divisions, and here the very weak is in the center. Right? Okay. And now what I can do? Now I'm thinking about, instead of 2 other, I'm thinking about using some strategy in let's say 2 decreasing. And I would like to persuade you that actually moving to 2 decreasing will not help. Actually, in some sense, it will even hurt you. Why? look at what's going on if I'm using a strategy against two other, if I'm using a strategy of the type HLH. You see what I mean here. HLH, the very strong is here, the strong is here, and the weak is here. And now I conduct some intuitive calculation where this calculation actually is defended in the paper with a very precise calculation, but I think that it's nice, we find it nice, that it is captured also by some sort of a very symbolic calculation. So HLH against HHL, so the very strong will beat the strong, the L will lose against the very strong, the high, the strong will beat the low. So here you will get average of 2 points, or almost 2 points. Let's say here, HLH against HLH, then it's 1.5, and so on. HLH against HLH, so I will, a tie here, a win here, a lose here. The average here is 6.5 divided by 4 is a little bit more than 1.5, and usually it's always the case, by the way. There will be a strategy in the cell that against uniform cell will get at least 1.5. And usually it will be a strategy will get a little bit more than 1.5, and that's what you get here. Now, let's say that I'm thinking about strategies in which in decreasing. So very strong, strong, low. And now very strong, and now actually this is a key to the understanding of the point. HHL against HHL. This win. The very strong beats the strong. The low tie with the low. But now comes the main point, which is the high here loses to the very high. And that's actually the key to the calculation, because actually when there is a loss, there is a waste here. There is a waste here. If you use the decreasing, you waste a strong division against a very strong. That's absolutely the opposite to what we have seen before. And actually, that's the key to the calculation. For example, HHL against this, you will win here, you will lose here, you will lose here, and so on. We do the similar calculation, and we get that then you get only 6 divided by 4, which is strictly less than 6.5 divided by 4. And that's the intuition why 2 decreasing is not better, actually even worse, than 2 other against 2 other.
So here, rather than calculating exact best view in this slide, you partition the cell into a smaller cell and calculate a kind of best reply.
It's not best response, no, because it's not best response against each of them. No, absolutely not.
As a part of the model to replace best reply against.
Right, that's what it's. You're absolutely right, and that's actually the reason that I presented here. That here, actually, I'm not talking about the language of best response. I'm talking about really language of the categories, and I'm demonstrating that exactly. In some sense, I do it here because I think that that's the right way, in some intuitive sense. Okay, but it is captured by the exact calculations that you suggested. I agree with you. That's interesting. Okay. So that's by the way, the two other is also a global equilibrium, but in this example. How does it relate to Robertson and Hart? It's very different. Actually, now what Sergio and also Robertson showed is that the mixed strategy equilibrium for this game is basically the following. It's such a mixed strategy such that the marginals on each of the battlefields will be uniform, 0 to 2n divided by 3. That's the result, which is interesting stability by itself, and we don't deny it. But of course, it's a very very different stability than the stability that we get, because if that's the case, then the expected number of battlefields is 1.5. Versus in our case, of course, it's always 2. So it's absolutely different than the Sergio Hart and the Robertson characterization. Okay, let me just mention very briefly the second example. The third example is what we call the tennis coach problem, but the second example is a game, actually, it's a game which was analyzed by Bob Rosenthal. Actually, this was his last paper that was completed by Sentes after his death. This is a three-object all-pay auctions, one of the early papers of this type. So the game was there are three objects up to for sales and two bidders. The bidders are expected pair of maximizers. Each receive capital M if he wins, but now you need to win two objects out of the three. So it's like that you have three states, and you have to win two of the states in order to be a president, and you blah, 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 blah. So each bidder is allowed to make three bids. He pays all the bids, so it's all pay auction. He makes, regardless of whether or not is the winning bid or not. For each object, the highest bid wins, and the tie is broken randomly. In the case that no one bids on the object, each bidder receives the object with probability 1.5, and so on. We did put a bound. Strategy is a triple of three non-negative integers, each between 0 and capital T. So there is some bound here on the what you can invest, and we have some constraints which I will not get into it now why we needed them, but that's basically the game. That's the game. The edited game. There are two dimensions here in our analysis. The first is the number of positive bits, which could be 1, 2, or 3. And the second is, and now comes actually another type of dimension. So I'm bidding. So I can bid any number between 0 and t. How do I think about it? I think that it's quite natural that I don't think about a particular number, but I think about whether to bid high or low. Maybe I think about very high, medium, low, very low, but this would be more details about in the computation. Just to demonstrate, we split the bits into high, above the average, above the m divided by 2, t divided by 2, and t is the bound actually, m is the size of the price. So okay, so the combinations. So we split the bits into two classes, low and high, and the three dimensions that the three values in the second dimension that we allow are L, namely low in all three fronts, all three bits are low, high, all three bits are high, and mix. Two are low and one is high, or two are high and one is low. And now comes a proposition which again, it's actually was even more difficult for us to prove technically, which is that there are actually two MD equilibria. Both are not global, and these are 3 mix and 2H. Let me talk for a second about 2H. So 2H is the mode of behavior. I bid only about 2. I completely ignore the third. That's an MD equilibrium, and it's not a global equilibrium because of the following very trivial point, which is there is a strategy in 3 mix. So I'm changing the two values, which is better than 2H. Why? Because if I know that Inku is bidding 2 in 2H, namely he ignores completely the third bid, then it makes sense that I will move to 3 mix and will put 1 in the bid that I'm completely ignoring. Now, this is not captured in the edited game. Why? Because this idea of actually moving to 0 to 1 is actually you have to actually to put it in a formal model as a third dimension, and this dimension does not appear in our analysis. That's the reason that 2H is not a global equilibrium. But if you don't think about this dimension and you just think about how many bits to put and whether to put all high or all L or some mix, then you just don't think about this consideration. Therefore, the fact, so some people may say the prediction of 2H, it does not make sense. Maybe it does not make sense if you do put, if indeed you think about the third dimension. If you don't think about this third dimension, I think it makes sense. And actually, this distinction is nicely captured by the fact that 2H is not global, and so on. And again, this prediction is very different than the equilibrium characterized by, in this paper by Rosenthal, which is, I will not get into it here. 10 minutes, so let me just talk about actually some points in the last section of the paper. Product games. Product-edited games, these are actually games where the category, as I said before, there are two components in the paper. One is that the language of the cells, the categories, and the second is the multidimensional. If I ignore the category, and I think only in the multidimensional, then actually, first of all, I'm going back to the team theory in a sense, but I get what we call in this paper a product-edited game. Product-edited game is the case that the set of the strategies are strategies are vectors, and the dimensions are the value in each of the dimensions, right? So that's a product game. So D3 is the value in the third place of the value of the vector. And now for this type of games, so if we assume that SK, so S, the set S is a product set, product of SK, and if each of the SK is, for example, a closed interval of real numbers, and if the utility function is a continuous function and concave in each of the components, then we can prove, that's an example of a case where we can prove the existence of MD equilibrium. Again, an equilibrium in this case will be a cell, but a cell in this case will be a strategy. So in this case, it's much less interesting for us because again, it's not a categorical, but still it's covered. And now the proof actually is a good exercise in exam because you construct a correspondence in the following way. That's a strategy. You ask yourself, along this dimension, what are the best responses to this strategy? So it must be because of a concavity. It must be some closed interval, concavity and continuity. You ask yourself, what is the best responses on this line? So this is again interval. And the correspondence that you build is from this point to this box. This correspondence satisfies all the standard Kakutanis conditions, and therefore there exists a fixed point, which is equilibrium for this case. So this is just an example of existence that you can show. There is actually a nice application which is discussed by Romer in the early 2000, which is called the two-dimensional. Actually, this game was discussed by many people before. It's the two-dimensional Hotelling game. So the space of the policies is some box. Or let's say a unit square in this case, and all voters have some convex preferences, namely they have some single peak, and there is some distribution of the voters. And now, as you might know, that and there are two candidates. And the two candidates will wish to win, to get a majority. And as you know, this game typically does not have equilibrium. This game typically does not have equilibrium, but it has an MD equilibrium. And the construction of the MD equilibrium is actually, we borrowed a proof by Romer, which was meant to do something else, which is the following. What you do is you take any line, vertical line, and you ask yourself, where is the median voters best, peak along this line? So it's this point. So you get a line like that. It's not a best response, but it's like a best response. And so each point here is, again, each point here, this point is the median voter peak if he is restricted to points on this line. And the same we do here. And these two lines must have intersection, and this intersection is exactly MD equilibrium. And actually, Romer shows that generically it's not a Nash equilibrium. Asymmetric, let's keep it. Let me just mention that actually that's something that Michael Richter suggested to us. That's an example, actually, that's, in my opinion, it's a very nice example of a family of games where existence is guaranteed. It's basically some sort of supermodularity. Here there is, in this case, there is categories, but the categories, the set of strategies is a line. They are split into intervals, and if you have something like supermodularity, then you can use standard arguments, which are, I think, quite nice to show that MD equilibrium always exists. Let me conclude with something which usually I'm not a big fan of, which is mixed strategies. Again, let me emphasize, MD equilibrium, I said it, but let me repeat. MD equilibrium definitely is not guaranteed to exist. And let me again repeat, it's like that pure Nash equilibrium usually, so very typically does not exist. But usually the saving of Nash equilibrium for game theory of disembarrassment is by mixed strategy equilibrium idea. And let me just say, not that I believe that this is a very interesting concept here, but just to complete the discussion, let me say we can, of course, construct something which will be parallel. We call it mixed MD equilibrium. It's not completely obvious how to do it, but let me suggest the following idea. A mixed strategy, a mixed MD equilibrium will be what? It will be a belief about the categories that you are using. So it will be 1/3 high, 2/3 low. Let's say that there are H, M, and L, 3 categories. So probably it will be 2/3 high and 1/3 medium, 0 L. In what sense it will be equilibrium? It will be equilibrium if I look for best responses against what? Against 2/3 uniform high and 1/3 to uniform L, then I find best responses against them both in H and in M, full stop. Maybe in L, maybe not. So any category that appears in the strategy with positive probability has to be, any category has to include some best response against this type of very particular uniform distribution. What could be the logic of it? The logic of it could be that you don't collect information again about the strategies, but you do collect, it's famous, that there are the 2/3 of the people using high H and 1/3 using L, but you don't know exactly, you don't have more information about the distribution within the cells. And then something of this type makes sense. Again, for mixed strategy equilibrium, mixed MD equilibrium, you can construct some existing theorems, but I will not talk about it now. That's the conclusion. It's nothing to do with the paper. And that's in line of my, some of you have heard me saying it already more than once. That's in my line of my preaching that economic theory papers should not have any conclusion. They don't have conclusion. What is it? That's it's a secret. It's in Chelsea, in Manhattan.
So you started with cardinal block again with 6 properties. What's the MD equilibrium?
With the 3 dimensions, Again, empty equilibrium, there is no empty equilibrium for a game. There is empty equilibrium for given the edited game. But if we adopt these three dimensions, I don't know. I bet that it must include, if it exists, it must include 4 battlefields. But it's just a bet. No, I don't know.
So the game pool of 2,000 people that played the strategy game, what would be the best that you could have possibly done? So there was a winner, but is there something better?
You asked actually whether in this particular doesn't matter. You ask whether in this particular game, what is the best strategy against?
Well, no, against those 2,000 people, is there something better than the winner?
Okay, yeah, that's for curiosity. Actually, we did find it. I'm not sure about what I'm saying now, but because we did not run all the strategies against, but we did run with 2 TAs, different DTAs, we ran against most relevant strategies, and we did not find anything which is better than the one which was the winner. But again, that's a probability 0 event. Thank you.